We present our work entitled Modeling Indirect Illumination for Inverse Rendering. Given a set of posed images captured under unknown static illumination, we aim to decompose the shape and spatially varying BRDF to enable applications such as free-view relighting. This inverse rendering problem is often solved by minimizing a re-rendering loss that compares rendered images with input images. However, capturing under natural illumination often shows complex effects such as soft shadows and interreflections. Simulating these effects necessitates modeling spatially varying indirect illumination and visibility for environment light. Computing indirect illumination using physically based rendering is intractable, since recursive ray tracing is computationally expensive and increases the complexity of decomposing unknowns. Without modeling the indirect illumination, its effect is prone to being baked into the estimated diffuse albedo to compensate for the gap between direct rendering and the observed image. To this end, we propose a method that models the indirect illumination by an MLP network that maps a 3D surface point to its indirect incoming illumination represented as spherical Gaussians. The core idea of learning this network is to serve the outgoing radiance field as the ground truth incoming illumination of its reachable surface points. The outgoing radiance field can be reconstructed from multi-view images with off-the-shelf neural scene representation methods. Specifically, we first learn the SDF and outgoing radiance field of the object, both represented as MLPs using IDR. The surface normal is the gradient of the SDF. Then we draw sample rays above sampled surface points and train the visibility and indirect illumination MLP. These MLPs are frozen during forward rendering. To reduce the ambiguity of disentangling BRDF and incident light, we introduce a prior that a real-world object should consist of limited types of materials. This prior is imposed by representing SVBRDF as an encoder-decoder with a sparse latent space. Without this latent space, optimizing each surface point independently would yield noisy roughness. The forward rendering is approximated as the SG integral. BRDF and direct illumination are optimized by minimizing the reconstruction error between the renderings and the observed images. Now let's look at some decomposition and relighting results compared to the previous method. Here, we provide more results on synthetic and real data. Thank you.